We build these incredible reasoning engines, and then what do? We load them up like wagons and make them haul data around. LLMs are for reasoning and analysis, not data transport. Hi, I'm Rashed. I'm an engineer at Fabrics AI. Last time, we talked about the context engine and how we manage what's inside the LLM's context window, both within the conversation as well as the agentic loop. I mentioned inter-tool communication at the end, and I said it deserved its own episode. Well, this is that episode. But let's zoom out a little bit first. Enterprise environments can be messy. You've got SQL databases, monitoring platforms, ticketing systems, network devices, and legacy tools that nobody wants to touch. And your agents need to work with all of it. The problem is, most of these systems were not built with agents in mind. At Fabrics, we solve this with what we call the Universal Tooling and Connectivity Engine, or UTC engine. You point it at any endpoint, whether it's native MCP or not, and it creates an agent-accessible tool that it exposes via MCP. You don't have to wait for a vendor integration. But connectivity is only part of the problem. Even when your tools are connected, they each run in their own isolated environment. An MCP server for your database doesn't know anything about the ticketing system, for example. So when an agent has to do something that involves both, like querying a database, finding anomalies, opening a ticket, what happens? The naive solution is to route everything through the LLM. The database tool returns its results, the LLM reads them, figures out what's relevant, and passes it along to the ticketing tool. The LLM becomes a data shuttle. And honestly, that's expensive and it's slow. You pay for every input token and output token that an LLM generates. So if you're using the LLM just to read a bunch of data and then turn it around and send it somewhere else, you're really wasting tokens and time. What you really want is a shared execution plane where tool outputs can be temporarily stored and retrieved by other tools. Tool A runs, stores its output, tool B reads it. The LLM orchestrates but never touches the data. Zero transport through the model. And this works even with remote MCP tools. The UTC engine acts like a kind of proxy. The tool's logic still runs remotely wherever it lives, but the UTC engine provides a landing zone for that tool's output, and it's the same place that other tools might look for their input. So what we're doing is we're exposing to the agent what looks like a single MCP server with all of its tools. And that masks the complexity of just how it is that we connect to the tools below, and exactly how data is transferred from one tool to the other can be completely self-contained within the UTC engine, transparent to the LLM. That's a theme that you're going to see repeating itself a lot through this episode, where we're taking complexity that could live at the LLM and we're driving it down into the tool layer. Another example of that is scale. When building a POC agent, any engineer can build a tool that takes a list of targets as input and then runs through them one after the other to execute some sort of command. That works fine for 5, 10, 50 endpoints, but what about 5,000 endpoints? Now you need batching and parallelization and fault tolerance and distributed execution at a massive scale, and that complexity has to live somewhere. With the UTC engine, it doesn't have to live in the tool. You get it automatically. The tool stays simple. The infrastructure handles the scale. Now, I want to talk to you about tool wrapping because I think it's underappreciated. So although LLMs are really cool for their ability to compose relatively complex expressions, in an enterprise, you can't just give an agent unrestricted access to your systems. So instead of exposing raw tools, we wrap them in clean, constrained interfaces. But here's the thing, it's not just about security. We had a supply chain customer try the raw API access approach early on. They gave their agent direct access to the query interface of their massive ERP system and asked it to find delayed purchase orders. It was a disaster. The LLM got completely lost in the weeds. It spent 2 minutes hallucinating a complex join between the vendor's table and a shipping table that didn't even exist. So we pulled the raw access and we wrapped that exact query into a simple semantic tool that the agent could invoke. Now the agent just sees list purchase orders, and it passes in the status and the date range. That's it. Their failure rate went to 0 overnight. LLMs can write SQL, but the more complex the expression, the more likely it is that the agent will get hung up on a minor syntax issue. And I'd rather the agent spend its cycles sorting through the problem than the syntax. When you give the agent a well-defined semantic interface, you get two things. One, you constrain what it can do, which is very important for security. And two, you free up its reasoning for it to be able to think about the task that it's trying to accomplish. It's just another form of context purity, which is what we talked about last time, only it's applied at the tooling layer instead of at the context window. The agent gets a clean, focused interface. The complexity lives underneath. And honestly, that's a design principle, not just a feature. Driving complexity into the tooling layer is one of the most important architectural decisions you can make when building an enterprise agent. The UTC engine gives you the infrastructure to actually do that. So that's what we call hyperconnectivity. But here's the question I want to leave you with. Even if your agent can connect to any system, and tools can share data directly, how does it even know which systems are relevant to the task? In a large enterprise with dozens of data sources and a constantly evolving infrastructure, how does the agent build a coherent picture of the landscape in which it has to operate? That's what we're going to talk about next time. And honestly, I'm pretty excited about it because I think this is one of the most underappreciated problems in enterprise AI. See you next time.